Today, we're going to discuss this awesome work from Berkeley, DeepMind, and MIT, which is called Unisim, Learning Interactive Real-World Simulators. Before telling you how the method actually works, I thought we could start with a demo because I think it's like seriously impressive results. So the goal of this paper was to learn a universal simulator, and on the author's website, there's a demo where you could actually select an observation, right, and then also select a language action. And then the model would generate for you a simulation, right, of that action executed from that observation. So, for example, we could have a kitchen scene, right? And then we can, from that kitchen scene, actually select a couple of actions like wash hands, for example, right? So you would see that the model is actually generating a video scene where this human is kind of trying to wash the hands. Or you can be in the kitchen scene and maybe shut off the water, and then you would also see that the human is kind of creating that. So like in it's an interactive process whereby you have your kitchen scene, right, and then you also have a set of actions you can pick. You could do that with, for example, picking a ball, where now you would see that the human is kind of picking the ball, and now you can actually put carrots in the ball. So the human is generated of putting like a scene of a human generated putting carrots in a ball, or it can put the ball down. We can also cut the carrots, right, and wash the cutting board, for example, as a scene. And as you see now, the human is kind of washing the ball. You could also do it with, other scenes. So, for example, here's a scene where you have this plug and these buttons, and then you can say, okay, press left, and then the human is simulated to be pressing left, or press right, and then the human is simulated to be pressing right. You can also plug in a cable as another simulation where the human is now simulated to be plugging in a cable. This is also doable for like interesting scenes. So, for example, this is a scene. I can say, okay, go left. Then there's a simulation of going left. Go zoom in, for example, and then you see that the simulation or the model is creating a scene for zooming in, zooming out as well. So you would see that the model is doing that. Also for panorama scans, right? So you could see that here we can turn left, we can turn down, we can turn right, we can zoom in, and so forth. It's also interestingly to be done with a robot. For example, put a sponge in the drawer. So here it will generate a scene of a robot that is actually kind of putting that, and close the bottom drawer. Then the same thing happens. A scene is created where the robot, sorry, is closing the drawer. It can also have a robot moving up, moving left, moving down, etc. Or a Frank robot, for example, here is kind of opening an air fryer or picking up a cup, or picking up a ball, for example, and so on. So this is the output, if you will, of this amazing work. And what they have managed to do is they have managed to kind of learn an interactive simulation, right? So learn a simulation from the real world data, was it internet scale or even simulated robot data, as we will discuss. And then from that, they were able to kind of create an action conditioned simulation. So it's important to notice that this is all action condition simulation. So here, as you see, the action is open an air fryer in a specific scene, right? And then the model will generate that observation, which will do this. Now, so this is the output of this work, which I think is amazing, really. And now what we are going to do is we are going to try to understand how the authors have actually executed this, right? Like, how does this method work and why it actually works? So let's get started with that. And this is the paper. It's called Learning Interactive's Real World Simulators. This is an amazing work, really, done by these amazing authors. Right. So let's start with the main motivation, right? So, what is the ultimate goal of a generative model, right? So, from the point of view of the authors, right, like one of the ultimate goals of generative models is that to take ingest, large scale data, like internet scale data, and then have a generative model, right, which we would learn in this paper, it will be a diffusion model, and then at the output of this, we could simulate, right, many different things. So we could simulate scenes or observations, and these are video observations, right, of like a cooking person, a robot doing something, a car moving, and so on. So really, they believe that the ultimate goal of generative models is to actually build a simulator, or maybe one of the main goals is to actually build a simulator. Now, why would we be interested in building a simulator? Because with simulators, right, we could do very cool things. So, for example, if we have an accurate enough simulator built from real world data and it's interactive, so we can apply actions to it, then the human can, for example, use the simulator to investigate and interact with diverse scenes and objects, especially maybe in dangerous situations. So we don't, have the human face a dangerous situation. We could also maybe have robots learn in these simulations. And because the simulations are learned from real world data, then that can help in reducing the sim to real gap, simulation to reality gap, and reduce the physical damage, right? Like the physical damage that can happen on the robot. Um, what's also very exciting is that if you're able to build more realistic simulators, then you are able to build more realistic video game simulators. And this is a humongous market. So I think it is expected that this market would be 583.69 billion in 2023. Was expected it'll be like something like that in 2023. And this is like, and I think it's still expected to grow further in the future. So the idea is that if we are able to build simulations, we could allow humans to interact in dangerous situations. We can allow robots to learn in these simulators, and we can even build much better video games with more realistic behavior. Right. So how would we do this, right? So the point is that one way you could think about doing this is we would say, okay, let's take, all the internet data of videos that is available for us, right? And then let's just build one generative model, like for example, a diffusion model, which you can condition on some action to give you, a specific output, which is another set of observations or a video output given your action and your observation. So this could be possible, but the problem is that the data sets we want to use, they cover different forms of information. So let's explain that. So for example, if you are talking about text and image data, so paired text and image data, you would notice that this data has a lot of rich scenes, but it has little movement in those scenes. So, for example, you can get a very rich, weird scene, like an armchair that looks like an apple, for example, but it's very hard to see movement, right, in this data. And if we want to build an interactive simulator, we actually need the movement, and we also need the movement to be action conditioned. So, given an action, tell me what would happen. Otherwise, it wouldn't be that interactive. So that's, for example, if we want to look at the paired text and image data. If we look at the video captioning data, then we also notice that we have very rich high-level description, but also we have little movement that is happening. Similarly, if we look at like a human activity data, so for example, Ego 4D type of data, we would see that we have rich human actions, right? Like this is a stitching example, right? And then here is like a mechanical warehouse example. But you would see that there is a rich set of human actions, but there is little mechanical movement or mechanical knowledge in this type of data, right? So it's just a video of a human doing something, but there's not much mechanical information embedded in this data. And finally, if we look at robot data, right, so robot learning data, this is a rich set of robot actions, right, that could be in simulated worlds or could be in real robot worlds. However, we don't have much quantity of this data, although they are on increase, but we cannot say they are as high quality as the others, right? So you see here that all these different data that is available for us to use to build that form of simulator that we are looking for, right? They do exist, but they cover different type of information. Some of them are static with little movement or little mechanical movement, and some of them are not a lot in quantity, and we need to sort that problem if we want to use that type of data to build our simulator. So really, if we want to build the simulator we're talking about, what we need to do is we need to unify and align those data sources to create that simulator we all are looking for. So we need to align those somehow. We need to have a unified description of the actions of the scenes such that my simulator is capable of working successfully, such that my model can ingest this data and learn something meaningful from it, right? Okay. So let's start by understanding, right, what is a simulator? So as defined in this paper, they define a simulator as a model, right? So that's a model where you give it some state, which is like an image. So it's a model, that's a model, that you will give it some state, which is like an image, and can take in some action as an input, and produce a visual consequence of that action in the form of video. So the way they define a simulator, they define the simulator as a model which will take in some image. So input is image, which is the state, and an action, right, which will be textual in this paper, or mostly textual in this paper, to produce a visual consequence, which is a set of video or a video set of frames that will describe the consequence of this action applied in this state. So that's how we define a simulator, right? So in other words, we have a generative model, right? And that generative model will take as an input a state, an observation, an image, and an action, and then it will create a visual consequence for us. And that visual consequence is in a form of video, something that looks like this. Okay, so if we want to build a simulator, we want to build that form of generative model that will take state and action input, image and action, and create a visual consequence for me. Right. Now, when we dig deeper, right, we notice that the simulator learning is actually challenging because different actions give you different formats. So for example, we have language instruction in some data set, we have robot control in other data sets, and we have camera movements in other data sets. Those are the different action formats. And also the videos, they have different frame rates and therefore might not be very informative, right? So they might not be informative corresponding to that input text that we actually put in. So the first thing they do in this paper is they do a diverse data orchestration. So what they're going to do now is they're going to take different data sources that are available on the internet, and they're going to try to unify those different data sources into one unified interface or action interface where I can describe any form of action from this data. How do they do that? So if we start with the real world data of video, let's say we want to use that data set, we notice that real world video action annotation is extremely expensive. right? Like if you're gonna annotate on every frame what action we're gonna take manually by a human, that is gonna be extremely expensive. And now, why do we need the actions, right? Like you might say, why do we need the actions? Well, we need the actions, right? Because we are going to use or build an interactive simulator where it will take a observation image and then action and it'll give me a video output, right? So now the point is that the action is important. What action I am taking is important for me to become interactive simulator. So in order to fix this annotation problem, they actually use a simulation engine or data gathered from simulation engine like Habitat in order to render the actions. So I think this is the Habitat scheme, and they use specifically something called HM3D dataset, and that allows us to have a action annotated video. And also they use another source of data, which is called the language data, language table data, in order to train this universal simulator as well. So this is this paper here that they actually also use the data from. Now, how do they encode the actions, right? So now we gather this data, we have this data, how we're going to encode the actions. So if the text description is available, right? So if we have text description that is available, we're going to just embed that text description into a T5 model embedding, right? So we're going to just pass this text through a T5 model, and then this T5 model will turn the text into a continuous representation, right? And that would be the embedding of my textual action, okay? So if there's text, it's easy to tackle this problem, because if there's text, all I need to do is I would need to just pass this by a T5 model, and then my T5 model would convert my text into a embedding space, which is describing the action continuously. But what do we do when we talk about continuous actions? So now this is interesting. When we have continuous actions, right, what are we going to do? Because imagine you are talking about a robot, you know, and now the action set in that robot could be, for example, the position of the end effector, right? Like where you want the end effector to go next, how you want it to move in delta X, delta Y, and delta Z, for example, right? That's one representation of the action. However, these are continuous numbers, and we want to build a universal embedding so we can unify all those actions together to be able to use all this data to build my interactive simulator, right? So the way they do this is actually very interesting, and I think it's inspired by Gato type of encoding as well. So what they do is they first encode the continuous actions as text and they normalize them. So if you have a continuous action, like let's say number 3.14 or something, then you just encode that as text, and then you normalize that in order to make sure, you know, that the range is uniform across, all your actions. But now what is interesting is after you've done that, now you actually discretize your actions. So you discretize your actions into 4,096 bins, right? So you create a histogram, and that histogram has 4,096 bins, right? And each of your continuous action will belong to one of those bins, right? So I'm taking these continuous actions and then I'm discretizing them into 4,096 bins on a histogram. Now, why that's interesting? Because the way you can think about this is that this discretization has actually created new tokens for my continuous actions. So now I will have an additional 4,096 tokens, right, that are in my vocabulary for the continuous actions. So now I can encode my continuous actions as text. And therefore, rather than only having 32,000 tokens, I will have 32,000 tokens plus 4,096 tokens, which will give me 3,696 tokens in my vocabulary, right? So now what I have is I have created a new set of tokens for the continuous actions, and I can therefore deal with the continuous actions in a textual way. Now, another data set they use is they use real-world robotic data. So apart from only using, this data, so they're using this first two data sets, the habitat and the language table data, and they now also consider that they introduce a real-world robotic data. So in the real world robotic data, they use two main data sets. One is called the bridge data set, and this is the data set which has like demonstrations in a kitchen. And then they use the RT1 and they refer to RT2, but I don't think they actually used that data sets in the paper as well. So the RT1 and RT2 data sets have been like these big discoveries by, I think, Google, where they actually were able to build, those models that would transform text into a sort of actions for the robot, and they are able to ingest a lot of heterogeneous, right, actions for us. So how do they encode the actions from this data set, the bridge data set and the RT1 and RT2 data sets? So what they do is, if we have text, we're just gonna have that text to be a high-level action for me, and then again, I will embed it with a T5 encoder. And if I have continuous actions, right, what they do is they again encode normalize and then they discretize them into 4096 bins, right? As we have done before, right? Like as we've done in this previous slide, right? So what we're going to do is we're going to discretize and then also encode them into 4096 bins. Right, so now we have these two different data sets. So one is the simulation data where they use the habitat data and the language table data. They encoded text with the T5 model if it exists, and they discretize those actions to introduce these extra tokens in my vocabulary into a histogram with 4096 bins. And if you have real-world robotic data, such as the bridge dataset or the RT1 and RT2 datasets, they are doing the same. They are taking the text description of the task as a high-level action, and they are actually now taking these continuous actions and encode them into text and discretize them as well, so we would create these extra tokens. They additionally made use of one more, or I think two more sources of data. One is the human activity recognition videos. So they took data from Ego4D dataset, Epic Kitchen dataset, and something version 2 dataset. So here, what are those data sets? So those data sets are data sets of a human executing, like a specific task inside those data sets. So, for example, the human would be walking, the human would be cutting in some board, the human would be buying something, riding a bike, and so on. And these are very big data sets. So these are human data gathered from egocentric videos in Ego4D, or in Epic Kitchen, it's a kind of a kitchen data set where the human is executing things inside the kitchen. And something to something is also a human activity type of data set that human is doing something cool in the environment. Now here the actions in these data sets, they are different from low-level control and are mostly high-level action descriptions. So they are mostly like video labels, like, for example, a human is walking, right? Or a human is picking up a shoe or something like that. So what they are going to do is first they are going to convert the video labels into textual actions. So now they're saying, okay, my action that is taken in this video is actually the label of the video itself, right? So this is the textual information that has been transformed into an action. Now, then comes the second problem, however, because these videos might have different frame rates, right? Then it is not meaningful to just have that big textual action and the whole video, because maybe the video in a small part actually describes the relevant information for that specific action. So apart from only converting, the video labels into textual actions, what they are actually doing is they are subsampling the video to construct chunks of observations that capture meaningful actions. So for example, if we are saying that the human is walking or something, and there's a big scene and birds flying and so on, and then only the human is walking in a subset of these frames, then what they are doing is they are actually subsampling that when they give the action label a human is walking, right? So what they do in these data sets is that their actions are high-level descriptors or the labels of the video. How do they embed those? Again, using a T5 model to become a continuous action representation, continuous embedding, right? And then what they're doing is they're also subsampling the videos in order to construct meaningful actions from those videos as well. Right. And then the other source of data they use is a source of data which is like panorama scans. So here, when it comes to panorama scans, they make use of the Matterplot 3D dataset, which is a dataset that looks like this. So these are panorama scans, right, inside a house. However, the problem is that when you look at the panorama scans or these 3D scan data, there's no action in them, right? It's just a scan of the environment. So they artificially create actions. The way they create actions is by, truncating the panorama scan, right? So they truncate the panorama scan, and then they use the camera poses between the images in order to create an action. So, for example, if they want to create an action called turn left, what they're going to do is they're going to cut the panorama scan here and left, and then they're talking about the camera poses between the images, and that corresponds to an action turn left. Turn up similarly, turn down similarly, and turn right similarly. So now they took the panorama scan and now they made sure they are able to use this panorama scan data inside their environment or inside their data set to build the universal simulator they are looking for by also taking into account or creating a set of artificial actions: turn left, turn right, turn up, turn down. These are textual actions which again can be embedded with a T5 models. And now I think the last data set they have taken is the paired internet text and image data. For example, Leon, this type of data set. Now here, so this is a data set where you can actually have a pairing or describe any pair of text and their corresponding image data, so they can be done together. And now they take this as one additional data source in what they are trying to learn. And the way they do it is they treat this as a single frame. So it's like a single frame video, and the caption that corresponds to that picture is the action, which you can again embed in a T5 model. All right. So now they orchestrated this data in such a way every data set will have actions, either textual actions or continuous actions that will be transformed into textual actions by this binning I told you about. So you add these extra vocabulary tokens for your continuous actions. And if you have text, high-level text description, right, then you can just use that as the action corresponding to that video. Or if you don't have actions like in the panorama scan, what they've done is they created artificial actions in a way by saying turn left, turn right, turn up, turn down, and then cutting the panorama scan and reasoning about the camera poses. Okay. Now, so that's the figure from their paper, where now they say, okay, this is the Unisim model, which can ingest different types of data. As we said, it can ingest internet text, image, videos. It can ingest robot videos. It can ingest human manipulation, robot manipulation videos, simulated manipulation, navigation, simulated navigation, and panorama scans. And all you actually need to do is you need to make sure that you unify the actions in order to be able to embed them with a T5 model. So in detail, the data they have used looks like this. So you have simulation data, habitat HM3D language table data, simulation, real world robot data, bridge data, RT1 data, language table, real data, and miscellaneous robotic videos. So those are, they said in the paper that they are kind of proprietary data set that they make use of. They also made use of human activities like Ego 4D something to something, panorama scans, and also, this is the internet text image data and some internet videos, which they also do not fully disclose. During training, this is the weight they use for all of those different data sets when they are training their model. Now, notice, like, we remember what we said, right? So when we talked about the simulation data, we have made use of the actions in there, and then we embed them into T5 model. When we talked about real robot data, if we had textual actions, we just can embed them. If we have continuous actions, what we need to do is we need to bin them to create these extra tokens and then embed them. Panorama's human activities, we took the action label, which is the general description of the video as the action, and we subsampled the video to have relevant or informative action movements. And then in the panorama scan, what we have done is something like we artificially created actions: turn left, turn right, turn up, turn down. And when it comes to the internet text and image data, they just assumed that the caption is actually the action, and the video is the output, is just one frame because it's a picture. And now with this, we can have a unified action space, which is really described by text, if you will. And now what they're going to do is they're going to take that action space, right? So the action space for all of those things we said, and then they're going to take text tokens that describe the action, convert them into a continuous representation using a T5 model, concatenate them with the low-level actions, which we transformed into this binning thingy, right? And that way we have a unified action space. So what they've done practically is they created a unified action space by considering text as my action. Was it a temporally extended action whereby I have the one description for a video and then I subsampled that in case of the Ego 4D, or if I have the textual action saying that the robot is picking something up, but I also have access to the end effector positions, then I am embedding the end effector positions via this binning idea, and then I concatenate with the textual description, and then I will embed it in a T5 model. So now this way I have a unified action space that will allow me to make use of all this richness of my data in order to build my interactive simulator. So now we have one common action space for all this different data that I can actually use to train my Unisim. Now, when it comes to training the Unisim itself, what they make use of is a video diffusion model. Now, unfortunately, I cannot dig into all the details of video diffusion model. We can have separate lectures on that. However, the whole idea, what they are trying to do is they are trying to build a distribution, right, from which you can sample a next set of video frames OT. Okay, so that's the next set of video frames OT. Conditioned on the history, so that's the frame history, so all the frames so far. And instead of taking all the frames so far, they have kind of a window where they take the most recent frames into account as the part of the history and the action, right? So given the history and the action, which could be one of those actions we described before, right? Then you are able to predict a next set of video frames. So this is an example of it, or this is an illustration of it, right? So this universal simulator is nothing but a video diffusion model, and it will predict the next variable length set of frames or video given the observation from the past, i.e. the history, right? And also given the action AT minus 1, right? So, and then it will be able to predict OT. So the action could be, the position of the end effector, could be a textual action, could be a camera rotation. All this is accepted because we transformed all these actions into textual format, really, and we are able to deal with them by this embedding in a T5 models. Right. So you take this observation, you have the action to create the new set of observations, then you take this final observation, you can have another action like wipe the table, and you can create a new set of observations, and so on. So now the dotted arrow they have here, so this dotted arrow, they indicate that they are concatenating the initial noise. So because this is a diffusion model with the frame in order to create the next set of frames. Now, when you want to do long horizon interactions, so like when we want to interact in a long horizon way, what we are going to do is we are going to simulate these long horizon interactions by sampling autoregressively. So we sample autoregressively conditioned on previous sampled observations and run through this diffusion model, and that would give me what I am actually looking for in terms of the next set of video frames. Right, now to parameterize the model, they use a diffusion model. So when it comes to the diffusion model, their denoising model is given in this way. So epsilon of theta of the observation OT at the denoising step K, conditioned on the history and the previous action, is given by 1 plus eta epsilon of OTK history HT minus 1, AT minus 1, minus eta of epsilon theta T of OTK and HT minus 1. So the history, the previous history, such that the last observation is actually coming from this Gaussian noise. So the idea is that this is the denoising model, right? H is the history, A is the previous action, and this eta controls, the action conditioning leg. The training loss to train this model is provided in this way. So it's just the noise epsilon, which is a Gaussian noise minus your denoising process squared. So it's just the MSE error. And beta K is just the set of noise levels at different denoising levels, K. And then if you have done this and you actually have trained your epsilon theta, now what you could do is from the current observation, you can actually sample a new observation by using this equation where you take OTK and you do minus gamma K of epsilon theta of OTK KHT minus 1 AT minus 1. So this is the model we have actually learned here. And then we add to that some varying level noise with Gaussian noise with the sigma K, and OTK is a starting as well from a Gaussian noise. The alpha K is the standard decay we use in diffusion models. So now I know this is fast and not like fully explaining the diffusion model, but the idea themselves come from two papers. One is called Denoising Diffusion Probabilistic Model and Classifier-Free Diffusion Guidance, which of course they refer to in the paper itself, and you can actually have a look at it. We can actually make a separate set of slides about this. But what I would like you to get from this slide is they are just simply training a video diffusion model where the denoising process is given by this equation, the training loss given by this equation, which is thus the MSE loss. And now once you have that, then you can actually sample the sample the next observation by doing these denoising steps. All right. And if you want to get much more details on what or how diffusion models actually work, then I think these two papers are very useful. And we can make a separate set of lectures on the diffusion models. If you're interested, please write us in the comments below. Okay. Now, the architecture itself, so in terms of the architecture, what they are doing is they are using a 3D UNet architecture. They are also doing spatial downsampling paths followed by spatial upsampling paths with skip connections. They also have interleaved convolution and attention layers. They use temporal attention. And the model itself is 5.6 billion parameter model. And it turns out it needs 512 TPU v3 and 20 days for training. Right? So how does this architecture look like in details as well is provided in these two papers. So Imagine Video and also 3D UNet. And also this table 6, they tell us all the hyperparameters we have actually used. So we need 512 TPU v3s and we need 20 days of training. So this is a pretty expensive model to train. But now, since we've done that, now let's move to some experimental results on, what I showed you in the demo at the beginning was one of them, but also they have some experimental results they reported in the paper. So the first thing they are able to do is they are able to describe action-rich manipulation, right? So now after they finish training their testing, their model, what they are able to show is that the Unisim, it can support manipulation actions such as, cutting carrots, right? Or washing hands or picking up a ball or drying hands, right? It can also support like pressing left, press middle, press right, and plug in a cable, as we showed you in the demo at the beginning. It can also support this navigation on images like this. For example, we've seen this bridge where we can go left, right, up, down, and zoom out. And of course, we showed there you can zoom in as well. And also on panorama scans where you can go left, right, down, and also zoom in. They can also simulate long horizon things in this autoregressive manner that we described before from your diffusion model. So what you could do is you can, for example, say the first thing I'm going to do is pick up a can and put on top, right? So that's the first thing I am going to do. Then what I will do is I will take, this observation, and then I follow that by another textual action, like close the bottom drawer, right? So here the bottom drawer is open, and then what you see, this is the starting frame, and now what you're going to do is you're going to close the drawer, right? And then you can say open the middle drawer, right? So you again are going to start from here, and then you're going to open the drawer. So you're kind of auto-regressively, right? Generating those frames. And they show that you can actually do it to simulate it in 8 interactions auto-regressively, okay? So this is one thing the model could do, like pretty cool stuff. It could actually do this long horizon autoregressive generation as well, where you can give it an action, which is a textual conditioning, and then it will autoregressively take the last frame, pass through the diffusion model, create the new variable length video, and then it'll proceed. And also, it can have diverse and stochastic simulations. So here, for example, it's a scene, it's simulating a scene where it can uncover a pen, or it can uncover toothpaste, or it can uncover a spider, or it can kind of, uncovering a plate, right? But also here, it could, for example, put a cup and then put a pen, for example, inside a cup, and that's what you see here. Or you can say, put an apple, right, somewhere, and then that's also what you would see there. So you can say put cup or put pen, and the cups and pens of different colors, they are sampled, right, as a result of the stochastic sampling during the video generation process. Okay. So it also could do diverse and stochastic simulations. Now, what is an interesting application they have done of the Unisim, although you can see many varying applications of the Unisim, I think one very cool thing is to try to train a robot in a way, right? So what they have done really is they considered a long horizon planning as an application. So what they've done is they've taken a language instruction into Unisim, right? And then they sampled like 3 to 5 minute rollouts and about 10,000 trajectories. Then when they have sampled that, they've taken the final frame from those trajectories as the goal, right? And then they scripted language instruction as supervision, right? So kind of they did a relabeling process. So what they've done is they started with the language instruction and created the video. Now they took the final frame of the video and they said, that's my goal, and then the language instruction was the supervision, was kind of, the supervision of that video. So kind of you flip the problem. Now you are able to, have a video and that is describing, that video can be supervised by the scripted language instruction. And then what you've done is you pass that to a Palm-E model. And now what you are able to show is that using that, you can actually do long horizon planning in reinforcement learning. So this is an example, right? So this is a long horizon simulation. So you start in some place, right? And now you have your goal in another place. And now what you've done is you've taken this data I told you about in order to train a visual language model, right? So now this visual language model could take an initial frame, right, and the goal, and then it will be able to generate your language instructions. So here you see, it'll take a starting frame, it'll take the goal frame, right? And now it could actually generate, its own language instructions. So language plans that are generated by the VLM policy. So here you can say, move the blue cube to the the bottom right, slide the green circle to the top left, and move the yellow circle to the bottom left. So you start here, and your goal is to reach here, and then you have collected data from your Unisim and trained a visual language model policy, a VLM, which I think was Palm-E in the paper. And now what you are able to do is you're able to kind of solve this task of long horizon planning. And they actually also executed that on real robot, and then they showed that this actually works. So here, a VLM policy will generate the high-level actions, which are executed in the simulator, right? So it will say, this is the action. You would execute that action in the Unisim simulator, right? Similar to how they are executed in the real world using the language table robot. The VLM is trained on the data from the simulator, right? So how we train this VLM is in this process here, right? So we're going to take this language instruction, we're going to collect these trajectories, and then we're going to use those trajectories to provide supervision of a vision language model, where we take the final frame as the goal input, the initial frame as the original input, and now the goal of the VLM is to start generating these textual descriptions for us, right? And here again, we have like a simulation, but from low-level controllers, not just from text. They want to show you it also works in these delta X, delta Y type of controllers. And now, as we can see, that the RL policy can successfully complete the task of moving a blue cube to the green circle. So that's all. That's the paper. I would like to thank you for this. I hope this has been interesting. There are many things we can do to improve this work. So, for example, we need to reduce hallucinations because it can hallucinate random stuff. Also, it seems to me a bit artificial in how we created the actions, really. So maybe one way we could improve this is by dealing with no action kind of learning. We can figure out some solutions from that perspective. So I hope you like this paper. I think it's a very important discovery, and I was very excited when I read about it. So, and I really hope you can find some awesome applications for it. So with that, I will end, and I will see you next time. Thanks a lot.